See my screen?
Yes.
Okay, great. So in the next couple of 20 minutes, I want to give you a brief introduction about linguistic speech tracking by the brain. And I will start with a very, very general introduction to even just neural speech tracking. I know there are a lot of experts in the audience, but just to make sure we're all on the same page. So whenever you have an issue with hearing, the audiologist, which will test how much speech you can understand, can rely on an extensive test battery, which holds, for example, pure tone audiometry or sentence recall tests. And these tests, they have some clear disadvantages. Of course, these pure tone audiometries, they work with tones, and tones you cannot understand. And these sentence recall tests, they actually work with really standardized and controlled sentences, which is nothing like real listening environments. Additionally, if you fail on these tests or cannot perform these tests, then the outcome does not allow you to pinpoint the origin of the deficit. Is it situated more peripherally, and can the patient be helped with a hearing aid, or is it situated more cortically, where maybe language treatment is a better option? Additionally, there are also, another drawback of these tests is that they are not inclusive. Not everyone can perform these tasks. You need to have attention and you need to be able to give feedback. But sometimes this is not possible. Think about working with very young children or patients with coma, for example. So that's why our research group and many others try to go towards a more objective way of testing speech understanding, meaning that we look at brain signals to see or to try and see whether or not someone understands speech. And to do so, we rely on the phenomenon of neural checking. So very quickly, I know you've heard this yesterday, but whenever you listen to speech and you would meanwhile record brain signals, then you can actually trace certain characteristics of the speech back in the brain signals. And previous studies showed that using specific features of the speech, such as acoustics, they can really give you insight in how much speech you can understand. So if neural tracking to the acoustic feature of the speech is higher, the speech is better understood. But then comes the issue, does neural tracking to acoustics means speech understanding? Well, that's not necessarily the case, because we also observe like significant acoustic neural checking whenever you listen to music, or whenever you listen to the ignored speaker in a cocktail paradigm. So you cannot say that if you have acoustic tracking that there is a successful speech understanding. It might be that acoustic speech tracking is necessary in order to understand speech, but it's not a causality. So before we delve into the linguistic tracking stuff that I'm really eager to talk about, I want to first take a step back and go very conceptually about the methods that we use and how this method actually works. So basically, we have a participant coming to our lab and we make them listen to stories or podcasts. And then in the first step, we estimate a brain model. So we extract some speech representations. Think about the envelope, an acoustic speech representation here shown in the pinkish line. These can also be sublexical features. So sublexical features denote the onset of a word or a phoneme, and those are indicated by the pulses. So whenever, for example, here, whenever you have a phoneme, there's a pulse, and these pulses are always of the same height. And then you have the linguistic features. So basically, these are also features with a lot of pulses, but this time the amplitude changes depending on how much information the phoneme carries, but more details on those linguistic features later. So whenever you have extracted these speech representations, you have, of course, also the recorded brain responses. And then in the next step, you basically link those speech features with the recorded brain signals. And that's to obtain this temporal response function. In a second step, you actually have this estimated brain model. You will use this TRF, this temporal response function, in order to extract a measure of neural tracking. So first, again, you extract the speech features, and then you do a convolution with the temporal response function. A convolution is basically a multiplication over time. Just as a quick recap, so we have a feature here, we have a TRF. This multiplication over time or convolution works as follows. So whenever there's an impulse, you see the waveform of the temporal response function. Now, whenever the signals become more complex, you can predict more complex signals. For example, here you have two impulses next to each other. So the two TRFs are very close to each other. So the outcome of the multiplication over time, or this convolution, will be a summation of the two signals. On the other hand, these waveforms can also be out of phase. So there is like a cancellation of this wave here. Now, if you also vary the impulses height or amplitude, then you can also, this also has an effect on your predicted signal. So using this multiplication over time, we have actually our speech feature that we extracted. We have the temporal response function, which tells you how the brain responds to the speech feature. Using this multiplication over time, we're basically giving or predicting a brain response evoked by the speech. We not only have the predicted brain signal, but also the actual brain signal, and that allows us to calculate a prediction accuracy, which is a measure of neural tracking. It's basically a correlation between each channel of the predicted signal with the actual recorded signal. I hope this very brief introduction was brief enough for the experts, but introductory enough for all the beginners or for people who are unfamiliar with this method. The takeaway is you have two important outcomes. You have this temporal response function, which tells you how the brain responds to the speech features, and you have this prediction accuracy, which tells you how well the brain tracks the speech. It's the measure of neural tracking. And this you have for every, or both measures you have for every sensor that you used. So using this approach, I try to answer a couple of questions, and I will cover these three questions during the talk. So the first question is, which speech feature should we actually use whenever you want to investigate linguistic processing by the brain? And then the second and also the third is whether these speech features really reflect speech understanding, because we tested this via two different paradigms, and I would like to go into them both. So let's start with this first question. For this, we tested 29 young normal hearing participants who listened to a really long story presented in silence. At the beginning of my PhD, the first studies were published using linguistic speech features. So as a starting point, we made like a scheme of all the speech features that we were aware of that used linguistic speech features or other features. And we wanted to test whether these linguistic speech features at different levels, so you have at the phoneme level, so which characterizes the information at the level of a phoneme, at a word, or even at the level of the context. Whether these linguistic speech features actually explains more variance in the EEG signal, in the neural signal, on top of acoustical and sublexical features. Now, why is this important? If you look at speech features, they're all derived from exactly the same signal. And this causes that these speech features are highly correlated. So whenever you have a burst of acoustic energy, you know that the envelope is going to be like a high waveform, which symbolizes this burst. But at the beginning of this burst, there is a phoneme onset and also an impulse of how much information this phoneme carries. So if you would only test a linguistic feature, it is still highly correlated with the response to, for example, the envelope or purely the acoustics of the signal. So to make sure that we estimated linguistic tracking in a way that it's not biased by acoustic responses, we used a specific framework. I will call it the subtraction approach. So basically, we calculated two types of models. A complete model. This complete model contains acoustic speech features, sublexical speech features, so the phoneme and word onsets, as well as these linguistic speech features. And then we subtracted the baseline model, which actually included all control variables. So these acoustic features and these sublexical features. And by taking the difference, we could investigate the added value of these linguistic features. So how much does a model improve in predicting the neural response whenever we add these linguistic features on top of the acoustics and sublexical features? This way, although it's not the perfect approach, of course, this way we tried to minimize the bias towards acoustic responses. But you see that the responses to linguistic speech features are really, really, really small. So that's also very, very challenging. But using this framework, we applied it on all the existing linguistic features or features that were already discussed in literature. And then we observed that not all of them survived this approach. So we observed these phoneme linguistic features, so phoneme surprisal and cohort entropy, and these linguistic features at the word level, so word surprisal and word frequency, those were significant. So for the rest of my talk, or we focused, or the rest of the studies that we did, we focused on those 4 linguistic features. But for this talk, I will only focus on word surprisal because it's a very intuitive feature. If you want to know more details about the other features, that's content for the workshop. So basically, word surprisal is how predictable or surprising a word is given the previous words. So for example, here, this sentence, even in the darkest of times, if one only remembers to turn on the, it's not surprising, you're going to expect light, so the surprisal value of light is rather low. If it would be to turn up the music, that would be surprising because it changes the concept of, or the context of the sentence that you had in mind. So these previous results we obtained by looking at prediction accuracies. So by looking at whether the linguistic features improve the prediction accuracy, so the measure of neural tracking. But we also had this other important outcome of the model. So the temporal response function, which tells you how the brain responds. And for word surprisal, it looked like this. So you have a clear negativity around 400 milliseconds, which is really prominent for these central channels here. And it's strikingly, so this is very similar to the N400 paradigms. Even in this case, it's using continuous speech and not carefully created controlled sentences. So in this first study, we identified which speech features we should use. The second question was, well, these speech features, they characterize some linguistic information, but do they really represent speech understanding? So to answer that, we manipulated the amount of speech understanding by speeding up or manipulating the speech rate. And we did this in 18 young normal hearing participants. And in total, we had around 6 speech rates, and each speech fragment was around 10 minutes. So to give you an example, I hope, wait, I am quickly going to check whether my sound is shared as well. Okay. I hope you can still see my screen and hope you can hear this example.
Mary, ik wil je graag mee uit eten nemen.
So I'm Dutch speaking, so this is really slow speech. For some of you, it might be intelligible, but for our participants, it was understandable. So this was a slow condition, this was a fast condition. It's very difficult to understand. No participants actually reported that it was well intelligible. So what happens with linguistic tracking? What happens with this added value of these linguistic speech features? So the red dots here indicate the significant channels, or the channels which drive the topography to be significantly different from 0. And in the slow and normal condition, you see in these conditions that you see these red channels, meaning that the linguistic features do have an added value, but as it becomes faster and faster, less red circles, so this added value of linguistic features, it disappears. Then again, you can also look at the temporal response function, at how the brain responds. And then you see this. So although it's super noisy, because this time we only have 10 minutes of data, while previously we had 45 minutes of data. But you see in the yellowish tones, we see a significant negativity, which is only present for the slower speech rates, which were intelligible by the listeners. Also, this characteristic topography, it fades away the faster the speech becomes. So this gives us a first insight, like, okay, maybe linguistic speech tracking really gives an indication of speech understanding. But there's a big but, because this paradigm, it used artificial speech, so we artificially sped up the speech. So what actually happens with natural speech? So in this case, we did a new experiment with 19 young normal hearing participants, which listened to different fragments, Dutch, Frisian, and a scrambled word list, and then we assessed the effect on linguistic neural tracking. To give you again an example, so for Dutch listeners, this will be intelligible.
Vandaag gaan we het hebben over Jack the Ripper.
Then the Frisian story.
Så var Maddie dit bandet op 12 mei 2003.
So the interesting about Dutch and Frisian, so Frisian is spoken in the upper north of the Netherlands, and it follows a very similar grammatical structure as Dutch. It's nearly a one-on-one mapping, so that's why we chose Frisian. But the participants reported that they had around 50% of intelligibility. But this is, of course, subjectively rated. And then a last example is the word list.
Blijven mij in is, hun, is en nadien.
So all these speech fragments are spoken by the same speaker, and they are also spoken in a very natural way, aiming to preserve the normal prosody. Then, so we can actually, again, plot the same results. So we see added value of these linguistic speech features. So now we had only 7 minutes, and we only observe these significant channels for the Dutch story, but not for the Frisian nor the word list condition. Then in looking at the TRFs, we also see only this prominent negativity around 400 milliseconds for the Dutch story, but not for the Frisian or the word list condition. And again, this characteristic topography, it disappears whenever it becomes not intelligible. So this again gives us some insight that maybe linguistic tracking might be a good indicator on whether or not speech was understood. But there are some clear pro and cons. So because it's an indicator, or my results show that it might be an indicator for speech understanding. So it can really pinpoint understanding and not just hearing. The disadvantage is that you require lots of data. You need quite some participants, because currently we can only look at it on a population level. And also per participant, there's a minimum of 10 minutes, but I would give you, ideally, the more data, the better, because it's such a small effect, which makes it really, really challenging. But we're currently working on an approach to make this more robust, but it's challenging. So in my workshop, my goal is to really make you able to craft your own speech features, to make these phoneme segmentations, do these language models, so you can create your own word surprisal stuff, and you can apply this for your experiments, so that we can all accelerate science together. So yeah, that's it. I'm happy to take any questions.
Cool talk. Thanks, Marlies. We have a question in the chat, but the asker is going to ask themselves.
Hi, can you hear me?
Yep.
Yes.
My question was, when you were looking at the difference between the fast and the slow speech, did you also look at the differences in just the acoustic model to see if changing this changed the tracking of the envelope or the other acoustic features that you used?
Yes, good point. Yes, we did look at the acoustics as well. Maybe I can annotate. I'm trying to. So I'm going to. Hopefully you can see my drawing. Can you see it?
Yep.
Okay.
It's a great drawing.
Yeah, it's beautiful. So what we actually, anyway, what my point, I cannot proceed with this drawing. I am not technical enough, I guess, to manage Zoom. But anyway, what we saw is that's with speech rate. So this is increasing speech rate, and this is neural tracking. So in the beginning, we see an increase with higher speech rates. And if I'm not mistaken, this effect was also seen yesterday. So with higher speech rates in the beginning, there's higher acoustic tracking, which I think makes sense, because there are just more acoustic boundaries to track and to respond to. So your neural tracking improves. But then at the end, where it's super, super fast, we see again a decrease. And this puzzled us a bit. So we went digging in literature. And then we could form some hypotheses, but this is purely speculations, that this might be due to motor cortex involvement. So whenever you listen to speech, your motor cortex is active, and it syncs a bit to how your lips would move. But when the speech is so fast, you don't have this lip image, and you cannot mimic on how your muscles would be able to pronounce this. Hence, your acoustic tracking would be slightly lower when it's super, super fast, when it's unnatural to be pronounced. So I hope that's clear and it answered your question.
Yeah, that was great. Thank you so much. And it was a great talk. Thank you.
Thanks.
Any other questions? Ed, if you want to ask that, you're more than welcome to. I can unmute you, or I can ask it. If you raise your hand, you can ask, but if you don't raise your hand, I'll just read it. There you go.
Hi, Marlies. That was a really nice talk. I don't know. I think I've asked you this question before, just about kind of linking across the different levels of processing, where, you know, some of the time if you're calculating things like phoneme surprisal and so on, it's kind of word specific phoneme surprisal, whereas obviously the surprisal of a given phoneme will be affected by how likely that particular word was to come up and all that kind of stuff. So I don't know if you thought about that any further or have anything to say on that.
Yeah. Indeed, there are like lots of ways that linguistic features can be improved. We currently calculate phoneme surprisal for a word independent of the previous words. So that's indeed a drawback of the current approach. But there are papers, a fairly recent one by Broadbeck, where he really tried to see at which level these phoneme surprisals should be modeled, whether how much context windows, and whether it's more top down or a bottom up effect. I feel using linguistic features that it's a bit like our brain is not exactly the same as a language model. So there will be ways to improve this, but I think it's very challenging to do it really in the right way, because even if you take further context into account, how will it affect? Like, I don't know. I'm puzzled by this myself to craft the optimal linguistic feature. I think this is a good starting point, but yeah, because for example, for word surprisal, I've tried comparing different language models, n-grams, which are the most simple ones, which I usually use, RNNs, LSTMs, which are able to have like way more context than this simple n-gram model, using lots of participants and 45 minutes of data. I cannot find a significant difference between those three language models, although the complexity is really, really different. So my takeaway is like, this is a group, like linguistic features are a good proxy, but like, I don't think the brain is really a language model. I hope that answered your question.
Yeah, that's lots of interesting stuff there in that answer. Thank you.
I have a question if no one else has one. I know Tom is big on creation and patents, and I was wondering if your involvement or if the lab involvement in this sort of project sort of ends at like the basic science, or if you all are working on implementing this for audiologist or clinical practice, like to any degree, any level of degree.
Well, I'm not involved in any patents, so, and I'm also not really aware of all those things. So if you want to use this stuff, you can use this.
Okay, fair enough. Okay. Well, if there are no more, someone has a hand raised. Ola has a hand raised. Feel free to ask a question, Ola. Ola? Did you raise your hand, Ola? We can't hear you.
Can you hear me now?
Yo.
Okay. So my question was, in the I think last experiment you showed like the contrast between word lists and the continuous story, that the word list doesn't show like an effect of word surprisal. Like, have you tried like actively modulating the surprisal of words in the word list? Like in the sense that, you know, if I have like a list where I say like house, cathedral, bridge, elephant, or something like that, like the word elephant would be surprising in that scenario. And maybe that would be like a way we could disentangle sort of narrative surprisal from this sort of simplistic word model, just word by word probability. Is that something you've looked into?
It's not something I've looked into, but it's very interesting, because I think the N400-ish response that you will get using your like word lists, which are actually semantically related and then suddenly unrelated, those will yield a way bigger response than narratives. That's my gut feeling, because those, like, you are really manipulating it in order for the participant to be surprised, while it is not really natural. Like, no one is going to say to you that he just ate a sandwich with elephant. So yeah.
Yeah, I mean, I gave an extreme example now, of course, but I mean, you could use language models to like carefully sort of titrate the amount of surprisal in the word list, so it kind of matches that of a natural story, and then compare. Would you think the two responses would be similar, or there would still be some difference between the two?
Yeah. Okay. I made a wrong interpretation. No. I think then probably the effect might be similar, but it will be very, very tricky because you always need to be primed. And so if you're in word lists like house, cathedral, those words will probably have like similar word probabilities, or maybe like semantically they're in a very same category, and those artificial settings will be also very difficult to recreate in a naturalistic story condition, because in the naturalistic story condition we really have these grammatical structure with nouns and pronouns and verbs. It's interesting to think about, and maybe if you're really clever you can come up with a cool design. But I think it's worth to wrap your head about it, but I'm not 100% sure what the outcome will be. But it would be cool to check it out.
Thank you.
Yeah, I agree. I think that's a pretty cool idea. I think there's a little bit of stuff to like think through that, but I think that's a great idea. Thanks, Marley, for that. Or with that, I think we'll thank Marley virtually, at least, and move on for the sake of time. I'm going to steal the screen back from you, Marley.